Real-time transport protocol. The real-time transport protocol is a network protocol that provides end-to-end network transport functions suitable for applications transmitting real-time data, such as audio, video, or simulation data, over multicast or unicast network services. In this video, we explain how RTP and its companion protocol, RTCP, works. Real-time transport protocol runs on top of UDP. Specifically, audio or video chunks of data, generated by the sending side of a multimedia application, are encapsulated in RTP packets, and each RTP packet is in turn encapsulated in a UDP segment. Because RTP provides services, like timestamps or sequence numbers, to the multimedia application, RTP can be viewed as a sublayer of the transport layer. From the application developer's perspective, however, RTP is not part of the transport layer, but instead, part of the application layer. This is because the developer must integrate RTP into the application. Specifically, for the sender side of the application, the developer must write code into the application which creates the RTP encapsulating packets. The application then sends the RTP packets into a UDP socket interface. Similarly, at the receiver side of the application, the RTP packets enter the application through a UDP socket interface. The developer therefore must write code into the application that extracts the media chunks from the RTP packets. If an application incorporates RTP, instead of a proprietary scheme to provide payload type, sequence numbers or timestamps, then the application will more easily interoperate with other networking applications. For example, if two different companies develop internet phone software, and they both incorporate RTP into their product, there may be some hope that a user using one of the internet phone products will be able to communicate with the user using the other internet phone product. It should be emphasized that RTP in itself does not provide any mechanism to ensure timely delivery of data or provide other quality of service guarantees. It does not even guarantee delivery of packets or prevent out-of-order delivery of packets. Indeed, RTP encapsulation is only seen at the end systems. It is not seen by intermediate routers. Routers do not distinguish between IP datagrams that carry RTP packets and IP datagrams that don't. RTP allows each source, for example a camera or a microphone, to be assigned its own independent RTP stream of packets. For example, for a video conference between two participants, 4 RTP streams could be opened. 2 streams for transmitting the audio, 1 in each direction, and 2 streams for the video, again, 1 in each direction. However, many popular encoding techniques, including MPEG-1 and MPEG-2, bundle the audio and video into a single stream during the encoding process. When the audio and video are bundled by the encoder, then only one RTP stream is generated, in each direction. RTP packets are not limited to unicast applications. They can also be sent over one-to-many, and many-to-many multicast trees. For a many-to-many multicast session, all of the senders and sources in the session typically send their RTP streams into the same multicast tree, with the same multicast address. RTP multicast streams belonging together, such as audio and video streams emanating from multiple senders in a video conference application, belong to an RTP session. RTP packet header fields. The 4 principal packet header fields are the payload type, sequence number, timestamp and the source identifier. Payload type. The payload type field, in the RTP packet, is 7 bits long. Thus 2 to the power of 7 or 128 different payload types can be supported by RTP. For an audio stream, the payload type field is used to indicate the type of audio encoding that is being used. If a sender decides to change the encoding in the middle of a session, the sender can inform the receiver of the change through this payload type field. The sender may want to change the encoding in order to increase the audio quality, or to decrease the RTP stream bit rate. For a video stream, the payload type can be used to indicate the type of video encoding. Again, the sender can change video encoding on the fly during a session. Sequence number field. The sequence number field is 16 bits long. The sequence number increments by 1 for each RTP packet sent, and may be used by the receiver to detect packet loss and to restore packet sequence. For example, if the receiver side of the application receives a stream of RTP packets with a gap between sequence numbers 86 and 89, then the receiver knows that packets 87 and 88 were lost. The receiver can then attempt to conceal the lost data. Timestamp field. The timestamp field is 32 bytes long. It reflects the sampling instant of the first byte in the RTP data packet. As we saw in the previous section, the receiver can use the timestamps in order to remove packet jitter introduced in the network and to provide synchronous playout at the receiver. The timestamp is derived from a sampling clock at the sender. As an example, for audio, the timestamp clock increments by 1 for each sampling period. For example, each 125 U6 for a 8 kHz sampling clock. If the audio application generates chunks consisting of 160 encoded samples, then the timestamp increases by 160 for each RTP packet when the source is active. The timestamp clock continues to increase at a constant rate, even if the source is inactive. Synchronization source identifier. The synchronization source identifier field is 32 bits long. It identifies the source of the RTP stream. Typically, each stream in a RTP session has a distinct SSRC. The SSRC is not the IP address of the sender, but instead, a number that the source assigns randomly when the new stream is started. The probability that two streams get assigned the same SSRC is very small. RTP Control Protocol. Request for Comments 1889 also specifies RTCP, a protocol which a multimedia networking application can use in conjunction with RTP. The use of RTCP is particularly attractive when the networking application multicast audio or video to multiple receivers from one or more senders. RTCP packets are transmitted by each participant in an RTP session to all other participants in the session. The RTCP packets are distributed to all the participants using IP multicast. For an RTP session, typically, there is a single multicast address, and all RTP and RTCP packets belonging to the session use the multicast address. RTP and RTCP packets are distinguished from each other through the use of distinct port numbers. RTCP packets do not encapsulate chunks of audio or video. Instead, RTCP packets are sent periodically and contain sender and/or receiver reports that announce statistics that can be useful to the application. These statistics include number of packets sent, number of packets lost, and inter-arrival jitter. The RTP specification, RFC 1889, does not dictate what the application should do with this feedback information. It is up to the application developer to decide what it wants to do with the feedback information. Senders can use the feedback information, for example, to modify their transmission rates. The feedback information can also be used for diagnostic purposes. For example, receivers can determine whether problems are local, regional, or global. RTCP packet types. Receiver reception packets. For each RTP stream that a receiver receives as part of a session, the receiver generates a reception report. The receiver aggregates its reception reports into a single RTCP packet. The packet is then sent into multicast tree that connects together all the participants in the session. The reception report includes several fields. The SSRC of the RTP stream for which the reception report is being generated. The fraction of packets lost within the RTP stream. Each receiver calculates the number of RTP packets lost, divided by the number of RTP packets sent as part of the stream. If a sender receives reception reports, indicating that the receivers are receiving only a small fraction of the sender's transmitted packets, the sender can switch to a lower encoding rate, thereby decreasing the congestion in the network, which may improve the reception rate. The last sequence number, received in the stream of RTP packets. The interarrival jitter, which is calculated as the average interarrival time between successive packets in the RTP stream. Sender report packets. For each RTP stream that a sender is transmitting, the sender creates and transmits RTCP sender report packets. These packets include information about the RTP stream, including the SSRC of the RTP stream, the timestamp and wall clock time of the most recently generated RTP packet in the stream, the number of packets sent in the stream, the number of bytes sent in the stream. The sender reports can be used to synchronize different media streams within a RTP session. For example, consider a video conferencing application, for which each sender generates two independent RTP streams, one for video and one for audio. The timestamps in these RTP packets are tied to the video and audio sampling clocks, and are not tied to the wall clock time, i.e., to real time. Each RTCP sender report contains, for the most recently generated packet in the associated RTP stream, the timestamp of the RTP packet, and the wall clock time for when the packet was created. Thus, the RTCP sender report packets associate the sampling clock to the real-time clock. Receivers can use this association in the RTCP sender reports to synchronize the playout of audio and video. Source description packets. For each RTP stream that a sender is transmitting, the sender also creates and transmits source description packets. These packets contain information about the source, such as email address of the sender's name and the application that generates the RTP stream. It also includes the SSRC of the associated RTP stream. These packets provide a mapping between the source identifier and the user host name. RTCP packets are stackable. Receiver reception reports, sender reports, and source descriptors can be concatenated into a single packet. The resulting packet is then encapsulated into a UDP segment and forwarded into the multicast tree. RTCP bandwidth scaling. Maybe, by this time, you notice that RTCP has a potential scaling problem. Consider, for example, an RTP session that consists of one sender and a large number of receivers. If each of the receivers periodically generate RTCP packets, then the aggregate transmission rate of RTCP packets can greatly exceed the rate of RTP packets sent by the sender. Observe that the amount of traffic sent into the multicast tree does not change as the number of receivers increases, whereas the amount of RTCP traffic grows linearly with the number of receivers. To solve this scaling problem, RTCP modifies the rate at which a participant sends RTCP packets into the multicast tree, as a function of the number of participants in the session. Observe that, because each participant sends control packets to everyone else, each participant can keep track of the total number of participants in the session. RTCP attempts to limit its traffic to 5% of the session bandwidth. For example, suppose there is one sender, which is sending video at a rate of 2 megabits per second. Then RTCP attempts to limit its traffic to 5% of 2 megabits per second, or 100 kilobits per second, as follows. The protocol gives 75% of this rate, or 75 kilobits per second, to the receivers. It gives the remaining 25% of the rate, or 25 kilobits per second, to the sender. The 75 kilobits per second devoted to the receivers is equally shared among the receivers. Thus, if there are receivers, then each receiver gets to send RTCP traffic at a rate of 75/kbps, and the sender gets to send RTCP traffic at a rate of 25 kilobits per second. A participant, sender or receiver, determines the RTCP packet transmission period by dynamically calculating the average RTCP packet size across the entire session and dividing the average RTCP packet size by its allocated rate. In summary, the period for transmitting RTCP packets for a sender is, and the period for transmitting RTCP packets for a receiver is. If you want to learn more about networking concepts and definitions, don't forget to press the subscribe button. To be notified when our channel releases another video, click also on the bell icon. And don't forget to visit our website, networkencyclopedia.com.